Boardrooms across the globe are filled with flawless generative AI prototypes, effortlessly answering questions and seamlessly executing complex workflows. Yet when these same companies attempt to deploy those models into actual business operations, the systems collapse. This chart shows the current state of enterprise AI adoption based on the MIT NANDA Gen AI Divide Report. Despite towering enterprise investment, about 95% of organizations are getting zero measurable return. This failure starts with the pilot to production chasm, the first of 13 vulnerabilities. A demo works in an isolated meeting, but it fails in production because it is not connected to updated policies, access controls, or employee workflows. The underlying model is often mathematically sound. The failure happens because the organization cannot operationalize it. Treating AI as an isolated magic brain ignores its reality as a complex software architecture. AI projects fail when teams overlook the dependencies between the model and its environment. The language model alone is a fragment. It only generates value when the model, context retrieval, internal data, tool execution, and security protocols are tightly coupled together. To achieve a return on investment, engineering teams must map and mitigate 13 specific architectural vulnerabilities that destroy a system's viability. We start building our architecture at the center with the standalone foundational language model. The next point of failure is overfitting. This happens when a model memorizes the exact patterns in its training dataset, but fails when encountering the messy variety of real-world data. During testing, accuracy looks excellent because the system recognizes familiar data. But when you deploy it, the model cannot generalize to unexpected customer inputs, creating a false sense of reliability. This behavior stems from the model acting as a stochastic parrot, the third vulnerability identified by researchers like Bender and Gabru. Large language models produce fluent language by predicting statistical token patterns. They string together convincing sequences of text without any actual structural understanding of the underlying concepts. Because the model is just predicting likely text, it is highly vulnerable to hallucination, confidently stating false information as fact. If a customer asks about a refund, the AI might invent a 60-day policy simply because that phrasing is common in its training data, even if the actual company policy is only 30 days. A base model cannot distinguish between linguistic fluency and factual truth. On its own, it is architecturally insufficient for an enterprise solution. Engineers connect a vector database to the model, feeding it factual documents. But this introduces retrieval failure. Weak embeddings fetch the wrong document. The model receives this incorrect context and generates a confident response based on wrong data, masking the failure. Even with perfect retrieval, the system is vulnerable to stale knowledge. This happens when the correct document is fetched, but the database itself is critically outdated. The AI might lock in a $49 product quote based on an unversioned cache, entirely missing that the live price increased to $79 last week. Continuous user interactions reveal the seventh vulnerability, context loss. Memory design flaws or window limits strip vital metadata out of a conversation. A user might provide their order number in the first message and say, "Cancel it" in the third. If that session state is lost, the agent gives an incomplete response, requiring the user to repeat themselves. Even when the model provides a correct answer, it can suffer from grounding failure. This is different from hallucination. The claim might be true, but it lacks a citation to a trusted source. In an enterprise environment, an answer without a citation is useless for auditing. If an HR policy claim cannot be traced to a specific section and date, it cannot be verified. A reasoning AI model is rendered useless if the architectural pipeline feeds it unverified, outdated, or incorrect context. The architecture expands when we give the model agency, connecting it to external APIs and untrusted inputs to trigger live actions. This introduces tool calling failure. When attempting to execute a user's intent, the agent might choose the wrong tool or parameters. Text errors damage brand reputation, but tool calling failures directly modify production databases. The AI might trigger an unauthorized refund or delete a customer record instead of checking its status. Adding external data introduces the 10th vulnerability, prompt injection, which the OWASP Gen AI security project ranks as a critical risk. Prompt injection occurs when external, malicious text manipulates the model into ignoring its system instructions and bypassing safety rules. If an AI browsing agent summarizes a malicious web page, and that page contains hidden instructions to exfiltrate user data to an external server, the model may follow that command. Treating retrieved documents or web content as trusted inputs creates a security blind spot, allowing external actors to hijack the agent's permissions. Granting a model the ability to execute live actions without strict schemas and human approvals transforms a simple chatbot into a security vulnerability. We reach the final phase, deploying this integrated AI system and attempting to monitor its health in the real world. Teams often fall into an evaluation blind spot. A system that passes 100 clean benchmark questions during testing creates a false sense of safety. In production, real users submit messy and incomplete and multilingual queries. If your tests miss these edge cases, your demo will pass while your deployment fails. Over time, the system will suffer from model drift. Accuracy degrades because real-world data and user behavior evolve away from the original training baseline. This leads to the final vulnerability: silent failure. The IT dashboard shows 100% uptime and normal latency, while the AI quietly outputs incorrect or toxic answers. Traditional software monitoring checks if a server is reachable. It cannot evaluate the semantic quality or factual grounding of the AI's response. Standard monitoring verifies the server is running, even while the AI generates unverified legal advice or incorrect pricing. Non-deterministic systems require a new monitoring paradigm. Attempting to fix hallucinations or agentic errors by simply adjusting the text prompt is an exercise in futility. The problems are structural. To build resilience, the context layer requires architectural safeguards, like hybrid search and rigorous metadata filtering for retrieval. The agency layer demands strict tool schemas, role-based permissions, and mandatory human approval for sensitive financial or data operations. Lifecycle management must evolve from tracking server uptime to continuously monitoring hallucination rates and citation coverage. To achieve measurable ROI, teams must stop treating AI as an isolated oracle. It must be engineered as a securely bounded, rigorously evaluated component within a distributed software architecture.